Welcome to YouTube channel Tech Guru Gautam Prasad. This video is on DC shunt and series motor speed control. DC shunt motor control speed control can be achieved by simple method. So we are going to discuss the speed control of the shunt motor as well as series motor in this video. This DC current flow produces two fields, the main field and the armature field. The above two fields interact with each other and causes the rotation of the rotor or armature. The commutator facilitates the change of the direction of current in the armature winding at the appropriate time. So this is the setup in which you can see uh, you have got the DC source and you have a shunt field connected in parallel with the armature. This is the armature and this is the two are brushes uh, resting on the commutator. So let us recall the DC shunt motor's equation for the back EMF. Back EMF equation EB is equal to phi ZNP by 60A, where phi is the flux for each pole with uh, in measured in Webers. Z is the number of conductors, N is the speed of the motor in RPM, and P is the number of poles, and A is the number of parallel paths. So, among these lines, we can also compose it by I. In this case, here you can see in the picture that this total current is the sum of this is getting divided into two parts, ISH and IA. One part is traveling towards the shunt field, and the other part is towards the armature. So, the total current is sum of IA and ISH. So, that's what is written here. And we can also see here ISH is equal to, as the voltage V has been applied directly on this shunt field. So this is equal to current through this shunt field. ISH is equal to V upon RSH or E upon RSH. E is nothing but the V. In any case, IA is equal to I total minus ISH, that is equal to E upon RA. That is armature field current. Armature current is equal to this voltage V divided by RA. So that is it. This part should be very much clear to understand the speed control of the DC motor, be it DC series motor or DC shunt motor. So speed control of the DC shunt motor, let's discuss here. As we find it through the equation of uh, EB, that N is directly proportional to EB upon phi, and this implies that N is inversely proportional to phi, that is field flux. So if we increase the field flux, the speed will decrease. On the contrary, if we will decrease the field flux, the speed will increase. So this will be the scheme of control of speed, and also N is equal to K multiplied by V minus IARA, that is EB upon phi. So EB has been replaced by V minus IARA and divided by phi. So this implies that N is directly proportional to the amount of EB. So if EB increases somehow, the speed will increase, and if EB decreases, the speed will decrease. So that could also be the scheme of speed control of the DC shunt motor. The DC shunt motor speed can be controlled in two ways: by flux control method, and the other is armature control method, that is by controlling EB. EB equal to V minus IAR. This is what we are talking about. So this uh, the shunt field characteristic is like this. This has got a drooping characteristic. So normal speed is given by this, but this speed with field rheostat, when you are weakening the field, basically you are achieving the speed above the normal speed. That point should be noted. So if you want to achieve a speed greater than the normal speed or the rated speed of the motor, DC motor, then you should go for field control, field weakening control. Speed control of the DC shunt motor continues in this slide also. The speed torque characteristic, which has a small linear drop due to the second term RA effect and translates upward as the field is weakened due to the armature reaction in the figure shown. So, armature reaction is something that is the effect of the armature field on the main field, that is the field because of the poles. The demagnetizing effect of the armature reaction causes characteristic to somewhat upward and increasing torque and increasing load current. The working range of the torque uh, speed torque characteristic reduces with increasing speed in order for the armature current not to exceed the full load value with the weakening of the field. So this is very important to safeguard your DC motor, and that must be considered that the load current, that does not cross the value of the full load current in any case. So here is the characteristic, and armature reaction has been considered. There are three scenarios that has been shown here. IR3 is less than IR2 is less than IR1. So IR1 is here. Uh, that is the maximum armature current. So field control for the shunt motor in these three cases has been shown here. This is for N1, N2, and N3 at IR1, IR2, and IR3. These are basically the mm, uh, uh, resistance, the current through the armature. This is armature reaction is being considered. So one part of this drop is basically because of, let me take a pen. I would like to make you understand here. This portion, this drop it is talking about, had it been normal, it would have been this followed this path, the this one path, but it is following this path because of this armature reaction. So it is dropping. A part portion also goes for this armature drop, that is IARA. So that is also considered. That is also considered uh, as the effect in the speed, because ultimately this speed is EB upon phi. As because of IARA, this EB is affected, so the speed is also affected in that case. Here, the speed control of the DC shunt motor continues, but here, rheostatic control of the DC shunt motor has been shown. So, here, basically, the current passing through this shunt field is affected, and with the help of this field rheostat. As we have discussed, this main current, load current, is, uh, sourcing towards two parts. One part is going towards the field, and the other part is going towards the armature. I'm repeating that. No, the speed and the torque characteristic for this situation is has been shown here. For the normal field, it is this. For weaker field, it is this, and for still weaker field, it is this. So you can see all the speeds that you are going to get here is higher than the normal speed, because you are weakening the field by inserting resistance in the armature in the shunt field circuit. So, higher the resistance in the shunt field circuit, lesser will be the current and weaker will be the field, and hence higher will be the speed. Speed control of the shunt motor is also continued here. In the case of the DC shunt motor, an increase in the armature circuit resistance will cause more voltage drop in the form of IARA in the armature circuit, and so the speed is reduced. So here we have taken this resistance that is in the armature circuit. So basically, the drop in the armature circuit is happening because some voltage will be dropped here, and that voltage will not be available to this armature, and armature will get reduced voltage. So while it will get reduced voltage, so it will run on lesser speed. So the field current will remain same as because there is no resistance connected in the field circuit. This has been shown as the resistance because the field shunt field resistance is very high as compared to armature resistance. So it has not been shown in the form of a coil, but in the form of a resistance. It has got a fixed resistance of higher value. So the main advantage of this armature resistance control method is that speeds below the base speed down to creeping speed of only a few RPM are easily achievable in this case. So this will give you speeds below the rated speed of the motor. So this method of speed control therefore is employed where the speeds lower then the rated speed is required for the short period and only and also occasionally as in the case of the printing machines, cranes, hoists, where the motor is frequently started and stopped. And this method of speed control is also employed where the load drops off rapidly and decreases in its decrease in speed, as in the case of the fan motors or blowers. The next is speed control of the DC series motor. We are going to discuss here. This DC motor has been shown. This is the series field connected in series with the armature, as you can see here, and there is a resistance in series with the series field. So, as you are increasing the resistance in the series field circuit, the current is reducing, and when the current is reducing, the field is weakened. At the same time, your voltage across this armature is also reducing. So, what happens actually in the case of the DC series motor, an increase in the armature circuit resistance will cause more voltage drop in the armature circuit, and so reduce will be the speed will be reduced. The torque, which is proportional to the product of the armature current and field current, basically T is directly proportional to phi Ia. In this case, phi is also proportional to Ia, so T becomes directly proportional to Ia square ultimately, and will also be reduced torque will also be reduced with the increase in the armature circuit resistance, as increase in the armature circuit resistance will reduce the armature current itself, and that leads to the lower uh, armature torque, and the flux which also depends on the armature current. So in order to obtain the different speeds for the constant load torque, the armature current is kept constant. So the flux, the resistance in the armature circuit is increased to reduce the speed. So basically, below the rated speed, if you want to get the speed, you insert resistance in this form in series with the armature circuit or the field circuit as such in the case of series DC series motor. This is yet another discussion on the DC series motor. For the DC series motor, the maximum range of the speed control of about 3 is to 1 will be available depending on the load. And this method of speed control most economical for the constant torque drives. So in this case, constant torque drive, torque is constant almost, and constant torque drive is adopted. This method of speed control is employed chiefly for the DC series motors driving cranes, hoist trains, because such drives operate on intermittent duty, off and on, very off and on, they are operated. So here the speed and the torque characteristic has been shown. The torque is on the x-axis and speed is on the y-axis with no resistance. This is the line which shows the speed, and this is the when you add slightly lesser speed you are getting, and still lower speed with further addition of the resistance in the armature circuit. For DC series motor, this is the characteristic. This characteristic is speed is increasing very drastically in this case, as the field is also weakened at the same time when you insert the resistance in series with the armature circuit, because armature and field both are connected in series. So as the current through the armature is reducing, so is reducing the current through the field winding as well. So that is weakening the field and achieving the higher speed. So with this method, you are getting higher speed uh, as compared to, you know, this is the case of the higher speed with no resistance, with resistance, further resistance, you are getting this. But in the case of this, you are seeing a lesser value of the speed you are getting, because this is happening because, as you are inserting the resistance in the field winding, so it is also reducing the voltage across the armature. So the total impact is that it also reduces the speed. So here, speed control of the DC series motor is concerned, is discussed here, and here a field diverter circuit has been used. So basically, the current through the field winding is diverted through a small resistance, and and uh, and uh, and mm, current through this field winding is reduced. So it is this field is weakened in turn, and the speed is becoming higher. Thus, so by achieving the field flux can be reduced by shunting a portion of the motor current around the series field, and thus reducing the excitation, MMF, and weakening of the field. And this method provides speeds above normal speed because flux is reduced by this method. Lesser the diverter resistance, less the field current, and less the flux, and therefore more is the speed. And this method is convenient as well as economical and provides a speed range usually not exceeding 2:1. And this method of speed control is used in electric drives in which speed should rise sharply as soon as the load falls. Here also, the speed control of the DC series motor continues. In this method, we have uh, we have to discuss tapped field method of control of speed of DC series motor. So in this method, speed control of the DC series motor, number of tappings from the field winding are brought outside as it is illustrated in the figure. By reducing the flux, by reducing the number of turns of the field winding uh, through which the current flows. When all the fields are there in the circuit, the motor runs at the lowest speed, and speed increases with the cutting out of some of the series field turns. And this method is usually employed in electric traction. Speed control of DC series motor. Here, series parallel control of field winding has been achieved. In this parallel fields, field coils are field coil method used in the fan motor. Several speeds can be obtained by a regrouping of the field coils as illustrated in this figure. So there are two situations that has been shown here. And since the flux can be decreased, not increased, so the speeds above the normal speed can be achieved in this method and not below. The speed is minimum at the maximum value of the flux and depends upon the design of the field and its a saturation point. Saturation point has to be considered because every field has its own capacity of saturation, and that much only it can contain. And if you want to go beyond that, it will start creating problem by increasing the current level. So that is harmful. Speed control of the DC series motor continues here also. The speed is maximum at the minimum value of the flux, which is governed by the magnetizing effect of the armature reaction on the field as well. At higher speeds of the motor tends to be unstable and difficulties in commutation arise. The high speed is also restricted due to mechanical considerations as centrifugal force are set at high speeds. So high speed is very dangerous because of the centrifugal forces, windings may come out at the dangerously high speed in the case of series motor. So that has to be given a due consideration. Speed variation by this method is limited to the ratio of 4 or 5 is to 1. Creeping speeds can not be achieved by this method. The power output being proportional to Tn or EIA remains constant. So this is also called sometimes constant power method of speed control. So this method is therefore suitable where power of the load remains constant. Series parallel control of the DC shunt motor has been shown here. So two identical motors are taken and these two identical motors are connected to a common load. That is the situation, and the speed control is achieved by employing this scheme. Two speeds at constant torque are possible in this method, one by connecting the motors armature in the series and the other by connecting them in the parallel as shown in these two figures. So here two fields are connected in series, two armatures are also connected in series. Here two armatures are connected in parallel, but here two fields are connected in series. So this there are two situations in which, so when they are connected in series, the terminal voltage across each motor is V by 2, whereas when they are connected in parallel, it is V. Thus the armature control of speed is achieved. So higher the voltage, higher will be the torque. As we have discussed, if you are able to remember the equation, you can understand higher the voltage, higher the torque. Here the series parallel connection of the series motor has been shown here. So there are two motors connected to the common load here. The parallel control of the speed control, series parallel speed control of the two identical series motors. And this method is superior for the rheostatic control insofar as efficiency is concerned. It is, however, limited to two speed steps. The method is commonly employed for speed control of the series traction motors. So this method is employed in tractions locomotives. So here, this is series motor, first series motor, second series motor. They are connected in series. So the first series motor, its field, the second series motor, and its field. They are connected in such a manner that they are in series, and the voltage is applied between them. Here, the first series motor connected across the supply, and the second series motor connected across the supply. So these two series motors have been directly connected across the supply, and in these two situations, the speed will be different. As the full voltage is appearing across the two armature, two motors here, so the full torque will be developed here. But here, half of the voltage is appearing across this series motor and half across this series motor. So the torque will be halved in this case. So the speed will be halved in that case also. So if you liked the discussion, if you liked the video, please give a thumbs up to this video. Don't forget to do that. And if you feel like asking any question, do write in the comment section. I would like to uh, clarify your queries. And if you are not subscribed to this channel, Tech Guru Gautam Prasad, I will suggest you to subscribe so that you keep getting uh, new videos, new such videos in future. Thank you so much. Thank you very much.